In the last decade, a lot was promised with regards to self-driving car. But as we can see, it looks that we are not quite there yet. There are a lot of potential challenges, such as regulation, testing, infrastructure, insurance, legal issues. But I believe they're all solvable once the technology is proven to be working. And the bigger question is, what are the main challenges in our way there? Today, deep learning is the leading approach to the AI problems. And indeed, it has great achievements. And it is the technology that allowed Waymo, Google's self-driving car, to reach 10 million miles milestone recently. But still, even though it struggles with some very basic scenarios, such as left turns, merging into traffic, driving through crowded spaces, and other industry leaders had very unfortunate accidents that raised even more questions. So let's take a look at some of the challenges of deep learning on the way to full autonomy. When we think about self-driving car perception system, we usually think about object recognition. So if we look from a point of view of a computer, this is how a road looks with object recognition only. And indeed, it's really hard to understand what's going on in this situation. And even if we are adding more information about the lanes, the roads, the drivable paths, it's still really hard to understand what's going on here. We humans, when we look at the road, we see much, much more information, right? We can see that this guy on the right, he's not just crossing the road, he's skating, that there is a school on the right, that probably at some hours maybe children can get out of it. We understand that there is a bus stop and a train lane in the middle. So we humans have much more information when we deal with this situation. And in order to get to the human level perception, we need to be able to have a contextual understanding of the situation. We need to understand the basic rules of the game of what's going on around us, understand all the agents' trajectories and behaviors, and eventually, the most important thing, to be able to predict what's going on to happen the next second, because we, the human factor, are very unpredictable and sometimes even not really acting according to the rules. Another issue is weather conditions. And even we humans sometimes have challenges in driving through rain, darkness, fog, snow. And I think for the systems such as deep learning, because they lack the contextualizations and the behavior understanding, it's really hard to complete the missing pixels when the weather is a little bit harsh. And Uber Arizona accident that killed Elaine Herzberg when she was crossing the road with her bike during the night, it's a really good example of one of these issues. It is true. Potentially, self-driving car can have better vision than a human because of the abundance of all the sensors such as IR, LIDAR, radar. But as we heard just now in the previous lecture, it's really a hard problem to fuse all the sensor, and I would even say it opens another Pandora box. Moreover, we don't really know what the real situation is because most of the testing is done in areas with nice weather, such as California and Arizona. Another thing is that the deep learning is a very highly supervised system. And I think all the experts in the area agree that unsupervised is the holy grail. Jan LeCun recently said that supervised learning is the icing, while the unsupervised learning is the cake itself. And one of the problems with this supervised approach is it requires a lot of training data, which is tagged, structured, and representative. And the quality of the results, in many cases, very correlative to the quality of the training set that we are able to gather, and it's really not easy to gather such a good training set. For example, Waymo's pedestrian recognition is based on millions of annotated images, and probably all of us participated in gathering it. Another important challenge or problem is the transparency of the system. We have a car that gets an input from its sensors, and then it gets into some huge multi-layered network that does something and gets us an output. In most cases, the output is as expected, but sometimes something unexpected happens, and it's really hard for us to understand why. Sometimes the network misses a clearly visible tree and gets crushed into it. Or sometimes we miss a pedestrian that is crossing the road where he's not supposed to. Or we see or the system sees a stop sign, and suddenly, instead of stopping, it speeds up. Like, this is a very famous example of little modification on the sign, and suddenly the deep learning network confuses it or even misdetects it. And it's really dangerous situation that causes some trust issue among the manufacturers and eventually, I guess, the public itself. And the last thing that I want to mention today is the power consumption. We all know that probably the electric vehicle is the next wave in transportation. And manufacturers and policymakers have already agreed and committed to the effort of pollution reduction. But if you open a trunk of a self-driving car, you will see that it's like a small power plant. And it's all power that's required to drive that vehicle. The GPS, the maps, the additional sensors, the additional weight, they're all wasting a lot of watts. But if we go and look deeper, we will see that the computer that is running the AI algorithms hogs more than 40% of that power. And with such power consumption, it will be really, really hard or even impossible to get to mass production. So it is clear that state-of-the-art deep learning has great achievements and it's a great technology. But is it enough to bring the breakthrough required to get to full autonomy? It is clear that another incremental improvement is not enough. And we need here a technology that is capable of human-level perception, that doesn't require tagged training data. It works in any conditions. It doesn't require, as we heard today, HD 3D maps, and transparent and explainable, and all of it has to operate under low power consumption. And I would like to introduce here Corrigan's autonomous AI technology that addresses these challenges. A lot was invested in developing machine learning since early 50s, but still, brain is much more powerful than any machine learning that exists today. Cortica's autonomous AI leverages the power of the cortex and mimics the way our brain processes information and learns. It is based on 15 years of development, and it started at the Technion, Israel Institute of Technology. It is protected today by more than 200 patents and inventions, and we believe that it brings a real human perception. We living creatures generate representations in our brain. This is how we believe the brain works, even before we do classifications. And this is exactly Cortica signatures. We take the input and we represent it as a high-dimensional representation similar to what our brain does. When a baby is born, they do not require their parents to present them with a training set for every object that they want to learn. They do it instantly, autonomously, in an unsupervised way. They just observe their environment, they generate representations in their brain, and then they cluster all this information. They cluster objects that they saw, behaviors, events, everything without any supervision. And this is how Cortica's algorithms work, in a very, very similar manner. We just get a raw input from a camera or any other sensor. We generate Cortica robust and lightweight signatures, and then we apply an unsupervised clustering algorithms in order to generate clusters of objects, events, situations, and behaviors. Cortica's robust signatures and unsupervised concept creation algorithms yield nearly perfect object recognition and systematic coverage of edge cases. And here I want to show you some examples of Cortica's system identifying objects in harsh weather conditions. And while it's playing, I want to mention that we took a raw video from the Uber accident in Arizona that was published by the news agencies, and we just ran it through our system as is, and we saw that our system was able to identify the pedestrian 0.9 seconds before the hit. And this, of course, could have saved your life. As you can see here, it works very well in night, darkness, rain, fog, snow, night and fog, night and snow. And the next thing is the human level perception, the ability to predict. We have a system that is able to understand situations and leveraging a big data of unlabeled video to find similar situation and learn behaviors. And based on that, predict what is going to happen. Here, for example, we have an understanding of the situation that this bus is loading passengers right now. And the system is able to predict that it's not going to move forward. Or another example, a big obstacle that is on the lane, we can predict that the vehicle that is ahead of us is going to change lane. To us humans, it sounds like a very simple scenario, but for a machine, when it needs to identify all the agents, understand the situation, predict the behavior, it's a very complex task. Here, I'm showing the identification of a construction on the lane and the prediction at the bottom of our system, both of the vehicle behavior and the car behavior. We are using here a very simple map that doesn't have any information overlaid on top of it, and we, with our perception system, complete all the information, including lanes, including buildings, including people, including vehicles, and everything, and predicting the behaviors. Another thing is the power consumption. Our flat architecture is hardware agnostic, meaning it can run on any hardware, and it runs on existing accelerators, hardware accelerators, because we are using generic signatures, so it doesn't matter what task we are trying to solve, if it's object recognition, if it's prediction, if it's situational understanding or trajectory prediction, it's all running on the same signature, which saves a lot of power. We have a collaboration with Renesas, and our technology is implemented in their new car V3H chip. And it is a production-ready system that consumes 10 times less power than any existing solution in the market and in academia. It's consuming less than 0.5 watt. The transparency, we believe it's a very important feature because it makes testing much, much easier and gains trust. Our concept structure is fully transparent and explainable. We can pinpoint exactly which signature ID contributed to a certain result. And if we want to update our concept, meaning a model, we don't need to retrain the system. We just go back through our CDK, Cortica Concept Development Tool kit, and we just identify a pattern that caused the false positive, and we just surgically remove it from there without touching anything else. And if we see a certain misdetection, we understand what kind of pattern is missing. We just generate a signature for that pattern and add it to the concept. That's it. And this makes the testing much, much easier, as I mentioned. Sensor fusion, it was touched upon it, but our approach to it is to merge multiple sensors into single one lightweight signature. So basically the same way we generated a signature for a camera, we now generate a signature for all the sensors into one representation space. And then we use the unsupervised learning that was presented before, just with multiple sensors. So I believe with all the things that I've presented, that Cortica's autonomous AI has the breakthrough that is required to move us to the next level of autonomy. Thank you.